We are talking about mathematics today, specifically the anxiety that it creates amongst kids, parents, and even teachers, and how to correct it once and for all. I will prove it to you in this video that it's not a prodigy that can learn math, but any child at any age can understand the basics and create strong fundamentals to become confident learners. By the end of this video, you would understand the principles of how our brain works and creates connections to make sense out of mathematics. I have lots of demonstrations lined up for you that you can replicate in your own homes and then take these learnings to teach your kids any subject, be it physics, chemistry, or even languages. Hi everyone, if you're new to this channel, my name is Aparna. I've been a senior software engineer for more than a decade and I've had a fair share of math learning in my life. I grew up in India where academics was very competitive and I was doing PhD level math at the age of 16. As I was growing up, I've had my fair share of struggles with math and a little bit of anxiety. But one thing that always saved me was just trusting myself and telling myself that I got this. No matter how I've been labeled, I'm gonna come out of it stronger. Eventually, I became pretty good and got decent grades. But if I knew all the things that I'm gonna talk about today in this video, I think my math knowledge would have been even more superior. So that's why I wanted to make this video so our next generation, the kids that we are teaching, do not have to ever doubt themselves that they can't do math very well. Now, before I start and show you all the demonstrations I've lined up for today's video, let me explain why most people have this math anxiety. And I think it has something to do with the way our system teaches this subject. One, most of the teachers are not confident. I even know today, talking to elementary school teachers or even middle school teachers, they were never confident and they sort of just transmit that energy to their students, and it's very easy to catch on. Number two, there is a very huge emphasis on just memorization. Memorization isn't inherently bad. We all should know what 3 plus 4 is. It's 7 right away. But when it comes to bigger quantities and just manipulating many numbers, memorization needs some support. That is the support that I'm going to talk about in this video. And everything that I'm talking about in this video is science-backed. Now that we have PET scans, 3D imaging of brains, we can actually see why math anxiety even happens, and it has been proven time and again how to correct that. To explain how math and language works in our brain, let me show you this diagram. Now, here is our right side of the brain and this is the left side of the brain. We have multiple functions that are processed by different hemispheres of the brain. You can see most of the language, symbols, and abstractions are on one side, and things like subitization, spatial perception, and refined hand control is on the other side. Now, you may ask, what is subitization? It's also said subitization, whatever you want to say. It's just a fancy word for quickly understanding how many numbers are there in a certain group. So for example, if I showed you my hand, you'll quickly know that there is 3 quantity in here. You don't really have to count, but as the number of these pegs increases, it's harder to count, and your brain, all that it knows is that this quantity is more than the 3 that we saw, but we can't really count it so quickly. Another example can be a roll of a die. We never ever count how many dots appear on the face of the die because our brain is able to subitize that quantity. Now, the problem occurs in the traditional math teaching methods. The problem occurs when subitization, spatial perception, this is not able to connect to the math language and the symbols. Abstractions are not connecting to hand control. So a symbol is nothing but the 1, 2, 2000. If this symbol 1000 is not able to connect to an understanding of how much 1000 quantity is, like they don't understand that this is 1000, what happens is this connection between the right and the left brain gets damaged. In fact, when we don't do enough spatial perception exercises or use our hands in a refined way, this side of the brain can atrophy. And eventually, as the child grows, they have internalized that they are not able to make sense of the numbers. It's not the numbers they are not able to make sense of. It's this connection that they are not able to make between these two sides of the brain. And that's why it is so important to introduce the concept of concrete before abstract. So let's now understand from a very young age. Say there's a 2-year-old and we are trying to teach them math. Just think about this brand new human and how much they know about symbols and real quantities, their connection. So for example, what does 1,000 mean? The word 1,000 mean to a 2-year-old? Probably nothing, unless they've been very observant and there's a lot of thousands spread around, like in the real quantity around your house, and they've started to make that connection. My guess is that they don't quite understand what that means. And for that, let me just show that with an example. So for example, this is a 1,000 cube. It has these beads. It has these 1,000 beads. And now just to contrast, this is a 1 bead. This is just 1 bead. The two are very different in the way they look, not just the color. This one's heavier, this one's bigger. And this quantity is clearly very different. And the reason why I took this example was just to exaggerate and show how these two quantities can be so different. And I know that many of 2-year-olds don't have real access to something concrete like that. And I would highly encourage you to gather some materials, not everything maybe, but some materials, and some of them you can DIY. Some of them, if you don't have like 1,000 bead cube like this, you can even create something with just 10 by 10 dots on each side, and it'll be better than nothing. But my point here is that each child should be able to touch the quantities before they even begin to learn to write them. And in another example, you can see I have 1,000 cube, this is 100 mat, this is a 10, and this is a unit. So when the child is about 3 or 4 years old, we can start introducing to them these concepts. Like this is a unit, that's a 10, that's 100, and this is 1,000, and then just ask them to repeat and let them touch and manipulate them however you want. So this will give them a very good idea of a little bit of the understanding of our number system, the base 10 system, and eventually if they do advanced mathematics or computer science, this will also help them because the image is burned in their heads. This will also help them with the binary system, which is much more advanced. Usually you learn it in college or advanced classes, but learning about the base 10 system this way will give them a much more concrete understanding of any other bases too. Okay, now the next thing I want to talk about is subitization, or some people say subitization because it sounds so similar to subtraction, but it's a very important concept in understanding the fundamentals of numbers as well, because we use it a lot all the time. So for example, if I show this to you quickly, without really counting, you can tell that there are 4 pegs over here. But if I put all of them together, and just mix them up, because I put them in 4, so it was easy to see, but it'll be harder as the quantity grows larger to see that there are 8 pegs here. Now, why is subitization important? It's because there is a lot of manipulations that our brain is doing, and we don't want to spend a lot more energy than we need to in understanding the quantity. And for kids, it's extremely important for them to have a very deep fundamental of associating quantity with their symbols. And that's why as the kids grow older, the 0 through 9, we show them in many, many different ways. I'll put pictures over here in how many different ways the Montessori system shows these quantities. Another great example of subitization is the die roll. Anytime a die roll, say it's over here, you don't even have to count. This is a 5, and even a double die roll, you'll be able to tell that you got a 6. Now, this is why we play a lot of board games with our kids, because now their subitization memory is getting extremely strong, and when they have to deal with numbers in many different ways, they don't have to waste time counting. Another amazing example in the Montessori system is color coding. So this is a short chain of 8 beads. Anytime a child sees a stick of beads that is brown colored, they already know, these Montessori kids already know that this is 8 beads. They don't have to worry about remembering what to count and what number they have to use. So we are creating this balance of not wasting their time on certain things that they should already be knowing versus just using it for the manipulative that it needs to be. So for example, this bead chain is a great example of showing them the table of 8 in a concrete way. Or if I were to fold this over, this can also become 8 squared. And once you fold this chain over, this looks like a square, doesn't it? Right over there. I even have squares that go with this. It's in my bead cabinet. So the point is, have 2, 3, 4, 5, 6-year-olds complete mastery over number symbols and a concrete representation of those numbers, especially from 0 all the way through 100. They should be able to understand that if they have 8 sticks of 10, that will make it 80, and then eventually 10 sticks of 10 makes 100. So they are able to connect these symbols from the left side to the right side and understand that this symbol, this linguistic area of their brain is able to connect to the spatial area of their brain. That is extremely important. And this is why even in advanced mathematics, you'll see, do you remember algebra where they said x squared plus 2x, and if you have x's, you can only add it to the x's. You can't add x's to x squares. So you can have 3x squares, that makes it 3x squared, but you can only have 3 x's, they are separate. And why? Is because this is x squared and this is 2x. They are structurally different. They can't be added together. That's why in an equation, you have to keep x squares separate and 2x is separate. When it becomes 10x squares, it becomes this, or x cubed in this case. Every step of the way, if a child is able to at least imagine something concrete with a symbolic representation, their math life is going to get easier. I have this friend who mentioned that they're not very good with numbers, but they're very good with the hand. So they're a great hairdresser. And I just think that they were never given an opportunity to touch these objects that convert into math. And of course, when you're a hairdresser, you're able to practice on hair. Nobody will ever start cutting hair without really practicing on a mannequin or on someone else, because you were able to make sense of the instruction that was given to you by your teacher and convert it into, different lengths of hair. So that's why I feel like cutting hair would be pretty complex, but because you got this understanding of concrete and abstract together, say there is a technical term for a certain hairstyle that needs 3 levels of cutting, you got that understanding by touching the hair and doing it, manipulating it. You got better at hair cutting, and math is nothing different. You will get better at math if you're able to touch the materials and manipulate them with your own hands. And now in this next section, I'm going to show you certain very common mathematical concepts. For example, in addition, when you have to do carryovers, or in subtractions, you have to do takeaways. These are the very practical ways and concrete ways to do both of them. And the best part about this approach is you will do the manipulations a few times and then you can move on, or the kids can move on to the abstract representations. These are some 4-digit additions that my son did. He's only 4 years old, but because we had the manipulatives, he was easily able to understand it, do the carryovers, and get the right answers. And you'll also notice that there's a lot of color coding going on here. There's a good reason for it, so they can understand the units, tens, 100,000s as separate, but also learn to combine them. So this next section will be a demonstration of a couple of very common concepts. So here it goes. We're going to focus on this problem, 1702 plus 4,928. I've written it over here, and I also have the materials that we are going to use to illustrate how to do this problem. As you can see here in this light handwriting, my 4-year-old has already solved this problem, and that's because we have practiced with the materials. Now that we did the materials a few times, he is able to just add normally and understands the concepts of carryover very well. And in this example, I want you to focus on how I carry over using materials. And once you have practiced, or the child has practiced multiple times, they won't need so much material anymore. All of this does take up a little bit of setup time, but it is totally worth it because the kids consider this setup as a game. And here we try to put both the materials and the symbols on the same level so they can remember to associate these materials with the symbols. So let's get started. Now, I already have set up everything right here. So you can see this is 1000. These are 7 hundreds. 1, 2, 3, 4, 5, 6, 7 hundreds. And let me just put it in this proper orientation. Usually we'll make sure that the 1000 columns are lined up with the thousands, hundreds and tens and so on. And in this case, there is nothing in the tens. So there's a nice large empty space. There is 2 units, and in the second line there are 8 units. So 8 units right here. Now we will invite the child to come solve this problem with us. We will always make sure that they start adding from the units to the tens, to the hundreds and thousands. And this is another great way for them to understand why we always add from the units, because once they start carrying over, they will know that the carryover only works from this direction to that. And in Montessori, they even use a physical, I'm just using a microphone wire right here, but basically this plus this equals to. So for the equals to sign, they'll have some like physical delineation for the kids to understand that the answer will be here and this is the problem. So let's try doing this. So here is 2 plus 8, which the child can either count one by one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or many kids might at this point already know that 2 plus 8 is 10 because they might have practiced this before just with some simple addition practices. This work usually is done by 4, 5, 6-year-olds, and when they were 3 something, they were practicing their numbers, associating the quantities, sounds and such things. So here we have a 10, and the child can clearly see that these 10s can be replaced by a 10 stick. This and this is the same. So they'll just put the 10 here, and this in their brains becomes the physical act of carrying over. This exchange that we just did is carrying over. So now there is a 0 here because they already added this. So here there will be a 0 quantity. We can represent a 0 with like just an empty. Okay, let me just move it so there's more space to see the answer. There are many ways to represent 0. This is a pretty nice way to say that, oh, this one's empty, so we'll be having a 0 in the answer and the units column. This clearly is 30. Now we have 9 plus 7, 9 plus 7. So this will become 10, which can be converted using, instead of these 10s, we can carry over this and then put these 10 mats away. So what are we left with? Some 600. So the 600 goes here in the answer, and then the final number of thousands is also 6. So we can safely put it here. And as you can see, even when we did this without materials, the kiddo was able to get 0, 3, 6, 0, 3, 6, and 6 as their answer. Now, another interesting thing here the kids can do is when they have this equation, 1702 plus 4928, they can place the answer just the way they made this equation. And I'll show you with just the answer so we don't have to do this plus this. So let's go create this answer. We have 1, 2, 3, 4, 5. So it'll be 6,600. Let's go to the hundreds. 6,630. which means all they have to do is put a 30 over here. There is no units needed here because the units are 0. And if you notice the materials, these numbers, the smaller quantities are the ones being added, and even these cards become big when you put this bigger quantity. So somehow their brain can associate that these two were smaller quantities and this one was bigger. All of these details will matter to the brain, especially the younger ones, because this will give them another form of understanding of how smaller quantities are coming together to become bigger quantities. Now, this is really life-changing to a child who's not really understanding the concept of carryovers. And if they do this maybe 5, 10, a dozen times, they will understand that carryovers are not a big deal. It really is needed to add these quantities up. And another fun fact is we actually start with 4-digit numbers for these addition types, because then the problem is exaggerated, it looks more fun, and they have more material to work with. We actually make our way down. We introduce the 4-digit additions first and then work our way down to 3 digits and 2 digits, because this is just more exciting. So this is really that out of the box thinking. You don't have to always work from small to big. Just think about what will be enticing for the child, what would interest them more. And instead of thinking about these things as math and schoolwork, this is a game. That's why most of this stuff is called, even the vocabulary that is used is game, because after this level, once they are comfortable with the golden beads, and we want to start with the golden beads just because they are a really good physical representation of quantity. 6,000 is so many beads. So once we are done with this, we don't always have to lug around so much material. And the next replacement level to this becomes the Montessori stamp game. And this is why it's called a game. Here we have everything. I have like a shoelace for that little line that we used just now. But the thousands now can be just converted to these 1,000 stamps. Now that, the child understands that 1,000 is a large quantity, they don't need this giant cube all the time. This can be changed to these little stamps. But if you'll notice, the color coding is still the same. Units are still green, tens are blue, hundreds are red. And then when you start the next iteration, you go back to green for thousands, and then 10,000s become blue again, and so on and so forth. So the organization of color, just for the brain to understand this pattern and recognize everything, is still the same. So eventually these golden beads can be converted using the stamp game, and they even have the representation of zeros. So over here, instead of this empty container, we would have put a 0 here. It's very similar to what I just did. They will be changing, the ones that become more than 10s into these 10 stamps, just like we did with the beads, and play the stamp game. These are beautiful, high quality materials, and that's why it lasts a long time. The kids can play this game for as long as they want, and that's the beauty of using materials which are fairly organized. And what I love to do with these concepts is also open up my brain and understand how I can use materials in different ways. So it doesn't always have to be something that you can buy from Amazon. You can create your own materials and create these stamp games or any of these things yourself. And as kids grow older and the concepts become more complex, you can use some more homemade materials and have them practice that way. And that's why our next example is going to be a little bit of an advanced math problem that we've done in elementary or even middle school, and that is signed and unsigned integers and their manipulations. So I'm going to show that to you outside my house on the driveway. We're going to make a number line with chalk and have the kids move around that number line. So now they even have that spatial awareness, moving their bodies. So just think about how you can connect a symbol with body movement or hand movement and create learning opportunities in the math world. Make it a game, make it interesting, and kids will never have problems learning their math concepts. So let's go outside next and check out the number line game. To explore signed integers, positive and negative, we created a number line with chalk long enough so the kids could walk over the numbers and solve some problems. I presented the first example, as you can see here, -6 plus 4. And after she practiced once, my daughter came up with her own questions to solve. This physical movement of their bodies on the number line symbols helps them connect the concrete and the abstract. Now, because we decided that we found out that the distance of 0 to 5 and 0 to -5 is the same, I can write this. I can't write -5 equals to 5. That won't be right. But when we talk about distance, this is how we write distance. This is called modulus. Making those symbols, it's called modulus. So modulus of 5 is equals to modulus of -5. Which means the distance from 0 to 5 and 0 to -5 is the same. Next, we explored the concepts of greater and smaller along with the modulus sign. Because the number line is right in front of us and fresh in our brains, it was easy for the kids to answer which one is greater.
Boom. Yeah.
You get it.
Versus 3. Let's see. I'm -1. You are -12. Who's the winner?
You keep all the blacks, I keep all the reds. Why? I get it!
Yeah.
I hope this video gave you a good idea of the framework that you want to use when teaching math and even science and so many other concepts to kids. If you try to combine physical movements, concrete objects to their learning, the abstract side of the brain will take care of itself. I'm also working on a blog post where I have put down all the resources of where I learned these things. So if you want to dive deep into it, you can just refer that blog post. It will be linked in the description below. It has all of the YouTube videos that I've watched and the courses that I've taken to learn and understand these things for my kids. And some of the courses are free, some are paid. I'll put that information down in the blog post. But as you go through this journey, continue to learn and teach yourself so you can support your kids' curiosities better. If you want to learn more about my homeschooling journey and why I started homeschooling my kids, I'll leave a link to that video right here, and I'll see you in the next one. Bye.